I'm Riley Freeland with Corning Cable Systems Cable Research and Development Group. Here we have a data center simulation which shows the advantage of ClearCurve multimode fiber over standard 50 micron products. On this side we have an EDA, or equipment distribution area, which is where a switch or server would be. But instead of a switch or a server, we're using a bit error rate tester to analyze system performance. The BERT is the main component of the system, running at 10 gigabits per second. We also have transceivers on these evaluation boards at 850 nanometers, one for transmit, one for receive. And the last component is an optical attenuator used to simulate system impairments. These components let us analyze different fiber designs, hardware designs, cable, and the interaction with different transceivers. The display shows the screen of the bit error rate tester with bit error rate versus time. Right now we're measuring a bit error rate of 0, which indicates a fully functional system. If the error rate climbs above 10 to the minus 12, then that's enough to cause the system to crash and throughput to suffer. One way of introducing errors is to use an optical attenuator. Here we've decreased the power level, and as a result, errors occur. Another way of introducing errors is through a macro bending event. For example, a cable pinched tightly on a routing guide can cause errors. Or in an overhead tray or a tray under the floor, the weight of cables pressing on each other can cause a cable to buckle, and when that happens, errors can also occur. It's examples like these that can give ClearCurve an advantage over standard 50 micron fiber. On this side, we have the MDA, or main distribution area. This is for cross-connect. Other places where macro bending can occur is if a cable is pinched tightly in a routing guide, caught in a door, or pinched tightly in a tie wrap. So it's these kind of common macro bending events that ClearCurve can really help mitigate. They're also very difficult to diagnose and troubleshoot, and it can lead to significant downtime. Our last example shows the advantage of a ClearCurve multimode cable versus a standard multimode cable pulled through a pass-through port. This first jumper is a standard multimode. We've attached a load cell so that we can see how much force we're pulling on this jumper with. The gauge goes from 1 pound up to 10 pounds. As we increase the load up to about 1.5 pounds, the error rate rises dramatically, enough to crash the system. This is the ClearCurve multimode. It's attached to the same gauge. And as we increase the load to 1.5 pounds, we see no change in the error rate. At 2 pounds, 3 pounds, 4 pounds, still no change. Only when we get to 6 pounds or 7 pounds do we see the error rate increase. It's these sort of macro bending events that ClearCurve can help mitigate so that you can ensure that the system doesn't have any downtime. Here we have a demonstration of ClearCurve multimode fiber in a simulated data center environment. On this side, we have the EDA, or equipment distribution area, which typically houses a server or a switch. Instead of one of those, we're using a bit error rate tester to analyze system performance. Other components include optical transceivers, one for transmit, one for receive, and an optical attenuator. The system runs at 10 gigabits per second over 300 meters of OM3 fiber. The main screen of the BERT shows an eye diagram. The main things to note about the eye is that the middle of the eye is open and that it's black in the center. A big open eye indicates good system performance. This first jumper is a standard multimode. We've attached a load cell so that we can see how much force we're pulling on this jumper with. The gauge goes from 1 pound up to 10 pounds. As we increase the load up to about 1.5 pounds, the error rate rises dramatically, enough to crash the system. This is the ClearCurve multimode. It's attached to the same gauge. And as we increase the load to 1.5 pounds, we see no change in the error rate. At 2 pounds, 3 pounds, 4 pounds, still no change. ClearCurve can help maintain an open eye. So we've seen the eye diagram and how useful it is as a tool for analyzing system performance and observing these macro bends in cables. Let's consider the eye diagram in more detail. First, we have a bit stream, which is a sequence of bits, optical power versus time. That bit sequence is pseudo-random, which means that it will repeat eventually, but the ones and zeros are mostly random. We can label this as ones and zeros. And then we can break this down into groups of 3 bits, from a 000, 001, and so on, all the way up to a 111. These groups are then overlapped to form the eye diagram. This overlap tells us about the amplitude of the bits as well as the transition points. We can take this a step further and form a bit error rate contour. With this, the bit error rate is measured in slices around the eye center, and then points of equal bit error rate are connected by lines to form contours from 10 to the minus 6 to 10 to the minus 16. Here we have 2 examples. On the left is a 30-meter piece of fiber. The contours are very closely spaced and very open. There's a lot of area in the middle of the eye at a very low bit error rate. On the right side is a very long piece of fiber, 900 meters. Here we see the contours are much further apart from each other, and they close down in the center of the eye. There's not much margin in this eye for operating at a low bit error rate. We can compare system performance at our level of interest, which is 10 to the minus 12. One eye has an area of about 40%, the other about 13%. So one eye is performing about 3 or 4 times better than the other. We can take these contours and compare fibers as they're bent. First, we see a multimode ClearCurve fiber that's straight. This shows bit error rate versus amplitude and time. The eye overlaps the contour like this. We can compare that to a standard multimode fiber. We see that the contours are almost identical, indicating that these fibers have very similar bandwidths. We can now bend these fibers with 5 wraps at about a 7.5 millimeter diameter. The ClearCurve fiber had only 0.3 dB of loss, while the standard had almost 3 dB of loss. The multimode ClearCurve fiber showed very little change, if any, in the contours, while the standard multimode fiber showed a serious degradation in the contour shape. These are a lot more bowl-shaped, with the area at the bottom a lot smaller. Using our bit error rate test set, we can compare different fibers, cable designs, hardware, and the interaction with transceivers. We use a variety of measurements, including eye jitter measurements, bit error rates at the eye center, and bit error rate contours.